All right, so I'm going to work these problems out on a piece of paper so it makes things a little bit neat. The first thing whenever I'm doing any of these problems is I like to draw myself a little heating curve that I can use as a reference. Remember, there are basically two different types of parts, or two different portions of the graph. Whenever I have a change in temperature, I'm going to use the formula Q equals mc, which is the heat capacity or specific heat. And I'm going to have a delta T because my temperature is changing. Whenever I have a flat place on the line, that's going to be a phase change. So I'm going to use the formula Q equals my mass times the heat of fusion or the heat of boiling, whatever the phase is. So I'm going to put H phase. And I'll have to look that one up. So now let's go ahead and let's do the first problem. A cup of coffee, which is 140 grams, cools from 75 degrees down to a comfortable room temperature of 20 degrees. How much energy does it release to the surroundings? Well, the first thing I'm going to do is draw myself a little sketch. It's starting off at 75 degrees Celsius. It's ending at 20 degrees Celsius. So there's the line that it's going to be. So for this portion of the line, I'm going to use Q equals mc delta T. Now I'm ready to get the information out of my problem. So my mass is equal to 140 grams. And that's all the information that I have. And that's all the information I need, except for I need to go up into my heat constants on the top and find that it's 4.18 joules per gram per degree Celsius. And that's going to be the C value of liquid water. That's the information I need to be able to solve this problem. Now I'm going to substitute in what I know. I know the mass is 140 grams. I know the specific heat, or the heat capacity, is 4.18 joules per gram per degree Celsius. And my delta T, I need to calculate. Delta T is equal to 75 minus 20, which means 55 degrees. So now I'm ready to substitute that in my formula. Now, a handy thing is to cross off all the units that match. So when I'm looking in my problem, grams, I've got 2 of them. Degrees Celsius, I have 2 of them. I'm left with joules. So my answer will be a value of Q that's equal to a number in joules. It's the only one I have left. That also helps me make sure that I'm not grabbing the wrong unit in my answer. I'm solving for energy, and so I need to have joules as my unit. So now I'm going to put it in the calculator, and this just becomes a multiplication question. And the final answer I get in the calculator is 32186, and that's going to be joules. Now I need to look at my significant figures. In my question, I had the number 140, and I had the number 75 and 20, but there was a decimal point after 20 degrees Celsius. So I'm going to need to have 2 significant figures in my answer. So my final answer will be and there's my answer. All right, now I'm ready to go on and do question number 2. Suppose during volleyball practice you lost 2 pounds of water due to sweating. If all of this water evaporates, how much energy did the water absorb from your body? Express your answer in kilojoules. So the information I need to have here is draw my little sketch. And It's at body temperature, so I'm going to say it's here. We have a change in phase. It's evaporating, which means the temperature is going to stay constant. Because I have a constant portion in my graph, the formula I'm going to use is Q is equal to mH of the phase. Now the phase is evaporation. And I look up at the top here and it says heat of vaporization, which means evaporating or condensation, is going to be HV. My heat of vaporization for water is, and I'm just pulling this right off the top of the chart there, 2,260 joules per gram. And that's going to be my HF. Now, I do see some other stuff in my question here. I've got 2 pounds. Well, my conversion factor here has grams, so I need to convert the pounds to grams, which is where all that dimensional analysis or factor labeling is going to come in now. So I'm starting off with 2 pounds of water, and it gives me the conversion factor that 2.2 pounds are in 1 kilogram of water. I need to have my answer be in grams. So now I'm going to convert kilograms. So 1 kilogram, I'm looking at my conversion table here, is equal to 10 to the third grams. My pounds is canceling off, kilograms is canceling off, and I'm left with grams, which is the answer that I need. When I convert that, I end up with 909 grams. In this problem, there are 2 significant figures, because I started with 2.2 pounds, so that's going to be 910 grams. So I'm going to need this information in my question, and I'm going to need this information to answer the question. Now I just have to plug things into the formula. My mass is 910 grams. My heat of vaporization is 2,260 joules per gram. Again, my units cancel out here. I've got a gram here, I've got a gram here. I'm left with joules, which is the energy unit that I need. When I put that all in my calculator, I get an answer that will have a unit of joules, and that becomes 2056600, which is a whole lot of joules. My final answer needs to have 2 significant figures because of the 2.0 pounds of water. So my final answer will be and if you were using scientific notation, this would be the final answer. All right, let's go ahead. Let me switch pages here, and we'll do number 3. All right, for number 3, we've got, suppose that during the icy hot lab, we had 665 kilojoules of energy transferred to 450 grams of water that were at 20 degrees Celsius. What would be the final temperature of the water? Well, I'm going to go ahead and pull out some information. The first thing is I'm going to be using the formula because this is a change in temperature. So I'm going to use the formula Q equals mc delta T. And I can see that from the portion of the graph above. So I'm going to be finding out the final temperature of the water. I have the amount of energy. The amount of energy was 65 kilojoules. Well, all my conversion factors are not in kilojoules, they're in joules. So I need to convert that to joules. 1 kilojoule is equal to 10 to the third joules. I'm just using my chart for converting. My base unit this time is joules instead of calories or meters or liters or grams. So I put that in the calculator and multiply the 65 times 10 to the third, and I got 65,000, or, yep. Now, that's a pretty big number. I guess I'll use that, but I'm getting to the point here where I may want to convert these into scientific notation, but we'll go ahead and leave that in the long form right for now. So I've got my joules of energy that I'm going to need for my formula. My mass is 450 grams of water. And it looks like I'm pretty much ready to substitute things, except for I need to get the heat capacity of the water. It is water, so I don't need the heat capacity of ice. So that would be 4.18 joules per gram per degree Celsius, and that's going to be the C of water. My mass was equal to 450 grams. So it looks like I have everything I need because I'm going to be solving for delta T. So I substitute everything in. That's the Q, the amount of heat. There's my mass. My specific heat, or heat capacity. And then I'm going to solve for delta T. Okay, so using the same rule that I used before when I was doing these sorts of problems, I need to isolate my variable. So how I can get rid of this is dividing it by itself. If I do it over here, I need to do it over here. Now that makes this go away, and I've isolated my delta T. Now I'm going to go through and I'm going to make sure my units, my joules are canceling out. I've got my, that was a gram. Grams canceling out, and now I'm going to be left with degrees Celsius. Put it in the calculator, and the change in temperature will be, when you get it in your calculator, you get 3.556. The number of significant figures I need in this is 2. Which means 35 degrees Celsius is going to be my delta T. I'm not quite done there, because remember, that's the change in temperature. If it's the change in temperature, I have to add it to my starting number. So it started at 20 degrees Celsius. It changed by 35. Which will give me an ending temperature of 55 degrees Celsius. And that's that one. Let's go on to number 4. The heat capacity of solid iron is 0.447 joules per gram per degree Celsius, so it's giving us that heat capacity. If the same quantity of energy as number 3 was transferred to a 450 chunk of iron at 20 degrees Celsius, what would be the final temperature? So let me pull out the information we need. First off, I have a heat capacity, which is going to be C, of iron, which is equal to 0.447 joules per gram per degree Celsius. The other information I have is a mass of 450 grams. I have initial temperature equal to 20 degrees Celsius. And the formula I'm going to need is, because this is going to be a final temperature, the formula I'm going to substitute this into is we have a change in temperature. So there's my formula. So it tells me I also have the same amount of energy that was in number 3. Well, the question 3's energy was 65,000 joules. So now I've got all the different things that I need to substitute into this problem. My Q was 65,000 joules. The mass is 450 grams. The heat capacity is 0.447. And my delta T is what I'm solving for. Now I have to get rid of and isolate my delta T, so I'm going to multiply those two and divide by that. If I do it to one side, I need to do it to the other. That gets rid of this side. Now I've isolated my delta T, and I can solve that fraction. Delta T is going to be equal to Now, I look back into my question, and if you look at the numbers here, we've got a 450 grams, and we've got our 20 degrees Celsius. The 20 degrees Celsius has a point after it, so that's 2 significant figures. So I'm going to need 2 significant figures in my problem, because that looks like that's the smallest number. So that's going to give me 320 degrees Celsius. Gram is canceling off. Joules cancel off. I'm left with degrees Celsius. Now, I'm not quite finished, because we have to find out what the final temperature is. So my initial temperature was 20. And I'm going to add my temperature change, 320 degrees Celsius. And my final temperature change will be 340 degrees Celsius. And there's my final answer. All right, now I'm going to go on and do number 5. And I'm forgetting to write my little chart, so I'm going to write a chart for this one. I'm going to read my question. Suppose a bag full of ice, which has a mass of 450 grams, starts at 0 degrees Celsius, sits on a counter and begins to melt to liquid water. How much energy must be absorbed by the ice if 2/3 of it melted? So my mass is going to be equal to 450 times 2/3, because not all of it is going to melt. My temperature is not changing because I've got a phase change here. It's just melting to liquid water. So the formula that I'm going to need is the mass times the h of the phase. Well, looking on the front of my sheet, I can see that the heat capacity, or the heat of fusion, melting or freezing, is, so we're going to be using heat of fusion, 334 joules per gram. And the question is asking me for how much energy must be absorbed by the ice. Well, first let's find out how much ice is being used in this problem. 450 times 2/3 is 300 grams. That's really all I need to do for this problem other than just substitute things in. My mass that's being melted is 300 grams times the heat of fusion, 334 joules per gram. My grams are canceling off. I'm going to be left with a Q equal to a unit of joules, and that number is going to be joules. Now the number of significant figures in my original problem, I go back and I look and I've got 450 grams. I've got 0.0 Celsius. So that must mean I have two significant figures, which means my final answer will be or, and it's better in this case to put it into scientific notation, because that would have two significant figures. All right, number 6. A serving of Cheez-Its releases 130 kilocalories. And it gives us a conversion factor of 1 kilocal is equal to 4.18 kilojoules when digested by your body. The same amount of energy is transferred to 2.5 kilograms of water at 27 degrees Celsius. What would the final temperature be? So, I'll draw my little chart here. It says it's going to be transferred to water at 27 degrees Celsius. So there's my starting point. It's being put into the water, so it's going to go up. I'm just not sure how much. So I do have a change in temperature, so I know the formula that I'm going to use is Q equals mc delta T. So I'm going to go ahead and grab out my amount I need for the heat capacity of liquid water. So my C is going to equal 4.18 joules per gram per degree Celsius for water. My mass from the problem. My mass is a little bit of a problem because it's giving me kilograms. So my mass is equal to 2.5 kilograms. Well, I can't leave it as kilograms because my unit is grams in my specific heat. So I need to go ahead and convert that. So I'm going to convert that, and it's going to give me 2,500 grams as my weight. The next thing I'm going to look for is we're given 130 kilocalories. So that's going to be the amount of heat. So I have to have it in joules though. So I need to convert that. 130 kilocalories. I'm going to use my conversion table just like I always would. My base unit here is going to be calorie. So I'm to kilocalories now, and that's going to be in 1. It gives me the conversion factor of 1 calorie is equal to 4.18 joules. So my kilocalories are gone. Calories are gone, I'm left with joules. And when I put that in the calculator and figure that out, I get now the number of significant figures I need to have in this is 2, and that'll give me, so now I've got joules, which is the unit that's in my problem. I've got grams, and I'm going to be calculating for degrees Celsius, so I'm ready to go ahead and put these into my problem. So Q equals mc delta T. So my Q is my mass is my C is and I'm trying to find out my delta T. So I'm going to divide this side by itself. Now you can see I'm starting to take shortcuts. So I can get rid of this. I've isolated my variable, and now I solve that fraction. Which will give me a delta T of 52 degrees. You can double check, my grams are canceling off, my joules are canceling off. I'm left with Celsius, and that's what I needed for my temperature. I'm not quite done there because I need to figure out what the final temperature is, because this is what we needed to find. So I need to take my 52, or let's go with my 27 degrees, which is where it started, plus 52. Which will mean that I'll end up at a temperature of 79 degrees Celsius. So that's where that will stop. All right, let's do number 7. This is our last problem. It says if this same quantity of energy was transferred to 2.5 kilograms of water at its boiling point, what fraction of the water would be vaporized? So what we know is it is at its boiling point, so that's 100 degrees Celsius. So we're starting there. It doesn't look like our temperature is changing at all. We're just going through a phase change. So the formula we're going to need is Q is equal to our mass times the heat of vaporization constant. We do have some things to convert here. First off, it's giving us the 2.5 kilograms of water. That's information we have. It's at its boiling point, and we want to know the fraction of the water that's vaporized. We also need to grab off of our chart what is the heat of vaporization. Well, I can't leave my kilograms the way they are because I'm going to need grams in order to figure this question out. I'm also going to need to grab the quantity of energy that was used in question number 6. So my Q, and I'm going to grab the one that I already converted because I want to have it in joules, was 540,000 joules. So let's substitute what I know. I know I've got a Q of 540,000 joules, and that's going to be equal to, it wants to know what fraction of the water would be vaporized. So I don't know exactly how much that total amount's not vaporized. It says what fraction is. So I'm going to be solving for a mass. I've got my constant for the heat of vaporization, which is 2,260 joules per gram. So now I'm ready to go ahead and solve this problem. In order to isolate my variable, I've got to divide this by itself. And if I do it on that side, I need to do it on this side. That gets rid of this. These units are canceling out, so I'm going to be left with a mass in grams as my answer. I put that in the calculator, and I got 239 grams. Looking at my significant figures, I need 2 significant figures. So that gives me 240 grams as the amount that's vaporized. Now it says what's the fraction that's vaporized. So I'm not quite finished here. I have to find out what is the percentage. So if I have 240 grams that is vaporized, and I started with 2,500 grams, that'll give me 0.096 times 100 to turn it into a percent. And that will equal 9.6%. So with that amount of energy, 9.6% of my starting amount of water will be vaporized.